Welcome back to the next video, everybody. Today's video is going to be on categorical group objects. Some more talk about that. We'll talk about group objects and homomorphisms today. So what's a group object? So just from here on out, the composition law that we discussed in the previous video, that's going to be written multiplicatively unless there's some kind of confusion. Okay. So we have a category C with finite products. A group object in C, also called a C group, is an object G in C equipped with a multiplication morphism M from G cross G to G, such that the induced law of composition from G of T cross G of T to G of T makes G of T a group for every T in C. Okay, so we'll say a group object G is commutative if G of T is an abelian group for every T. So all these guys are groups for each T. And a homomorphism of group objects from G to G prime, let's say, is a morphism phi from G to G prime in the category C, such that for every T in C, the induced map from G of T to G prime of T given by G maps to phi of G is a group homomorphism. So basically it's a map on the group objects that descends sort of to an actual God's honest group homomorphism from abstract algebra class on these groups G of T for each T. Okay. A pair G comma M is a group object if and only if the associativity, unity, and inverse axioms from the previous video are satisfied. And as expected in this case, the unity epsilon and the inverse morphism inv are unique. G comma M is a commutative group object if and only if the commutativity axiom from the previous video is satisfied. Okay, so none of this should be shocking, but these are all good exercises to try. Let G comma M and G prime comma M prime be group objects in C. Then a morphism phi from G to G prime is a C group homomorphism if and only if phi lower star of the first projection times the second projection equals phi lower star of the first projection times phi lower star of the second projection in the G cross G points of G prime. Okay, of course, otherwise it doesn't make sense. And here phi lower star denotes push forward. So phi lower star G is phi composed G. So it's kind of the natural opposite to pullback. Okay. And so that is unwinding definitions. What does this say? Diagram theoretically. Our morphism phi from G to G prime is a C group homomorphism if and only if the following diagram commutes. So we have phi cross phi going from G cross G to G prime cross G prime. Down the right side, we have multiplication M prime, the multiplication map associated to G prime. Going down the left side, we have the multiplication map M associated to G. And then down the bottom, we have phi. Okay, this makes perfect sense if you think about the homomorphisms that you all know and love from basic abstract algebra class. Okay, let's see. So I really like this next slide. I think it's very helpful to think about. So suppose we have an object G and C, and instead of a law of composition M from G cross G to G, we have for each T and C a group structure on G of T, such that for each map F from T prime to T, the induced map, so F star from G of T to G of T prime, so the pullback map, is a group homomorphism. So, okay, so I know that for all of the morphisms in C from T prime to T, the G of T to G of T primes are group homomorphisms. I find that very easy to think about compared to abstract composition laws on, generic group objects, because I think of these as the T-valued points in G. Okay, this, if you have this setup, this gives a unique map, actually, M from G cross G to G, which induces the group structure on G of T for all T. In fact, you can recover M easily and its uniqueness from the given law of composition on the G cross G points of G. It's actually just the product in that given law of composition here. M equals first projection times second projection. That's a good exercise to check. It's actually an easy exercise, but okay. And so a lot of the above discussion can be summarized by saying the following sort of easy, nice, natural thing. Giving a group object in a category C with finite products is the same thing as giving a contravariant functor from C to the category of groups, such that the underlying functor from C to the category of sets is representable, meaning it's isomorphic as functors to a functor of the form T maps to G of T for some object G in the category C. Okay, so this, like I said, this is a great summary of a lot of what we just said in far less verbose language. Okay, so next time we will continue to discuss group objects and homomorphisms. We'll discuss kernels and co-kernels and things like that and how those work. And so thanks for watching, and I will see you then.